Alright, so let's look at some past exam style questions on electricity. So we've got some IV characteristics for three components. We've got a fixed resistor, a filament lamp, and an LED. So first graph, we can see we're getting zero current for a range of potential differences, and then we get sudden spike in current. That is characteristic of a diode of some kind, in this case an LED. The next one, we've got a straight line IV graph, which indicates we've got fixed resistance. So we've got fixed resistor, and by process of elimination, this one must be L. But we can see that with larger currents, we have a larger resistance, which is consistent with what we know about filament bulbs. Okay, so we've got a graph showing how current varies with voltage for four components. Which component is the resistance initially constant before increasing? So the first thing you have to know is that the gradient of these graphs is 1 over the resistance. So if we're looking for something where resistance is constant and then increases, we're looking for a graph where the gradient is constant, then decreases. And I reckon that one is shown by D. Okay, so we've got an electrical characteristic or an IV characteristic for a component, and we want to match it up to its resistance versus potential difference graph. So what I'm going to do is I'm going to identify which one's the correct one, and then we'll talk about how we get to this graph. So what I'm going to do is I'm going to break the graph up into three sections, essentially. So we've got the first section where it's behaving like an ohmic conductor. So resistance is the reciprocal of the gradient. So let's start with that. So we can see it's a straight line, so the resistance is constant, and it's also a really shallow gradient indicating we've got very high resistance at that point. So we already know it's got to be either B or D because we've got high resistance to start with. Now the slightly more challenging part comes in the second bit, because it's quite commonly thought that resistance is the gradient of an IV graph, and that's true a lot of the time, but actually in this situation it becomes not true. So you can see the red line and the green dashed line clearly do not go through the origin. So in order for resistance to be the gradient, we need the graph to be a straight line passing through the origin. So it might be tempting to say that in these sections that the resistance is constant, but actually if you calculate V over I during those sections, you'll find that V over I is constantly changing, and therefore the resistance value is constantly changing. But if we actually do that and you try a few numbers, what you find is the resistance decreases and then sort of levels off, which is what matches with B here. But what you won't find is that at any point on the red or green lines is resistance constant, which is how I eliminated D from the answers here. Okay, so a heater is rated 220 volts, 500 watts, and it's connected to a 220 volt power supply. When the heater is connected to a 110 volt power supply, what is the current and what is the power? So if we supply half the potential difference, we're going to end up with half the current, so it's got to be A or B. And remember, P is equal to I squared R, or V squared over R. So if we have half the potential difference, we end up with 1/4 of the power. And this is the reason if you take a hairdryer across to America, it won't work very well, because if you buy it in Europe, it's designed for about 230 volts, and if you hop over to America, it's now supplying it with 110, so you get sort of 1/4 of the power output, which isn't great. Okay, so we've got three identical resistors connected in series across a cell, and the same three resistors are then connected in parallel. Assume the cell has zero internal resistance and does not run down. What is the value of power of the cell with resistors in parallel and power when they're in series? Okay, so here's the equation I'm going to use to figure this out, V squared over R. So we're using the same cell each time, so V squared is not going to change here. It's the R that's going to change. So when they're in parallel, if we have three identical resistors in parallel, we end up with the total resistance being 1/3. If we have them in series, we're going to end up with R plus R plus R, so 3R. So we can see there's a factor of 9 difference between parallel and series. So you can see that the power in parallel is going to be 9 times greater than the power in series. We could also solve this by thinking about the current as well. So there would be a factor of 3 difference in current, and then I squared r, and you get the factor of 9 again. So you can use whichever logic you like, but you still end up with 9 times bigger with a parallel setup. So what is the meanings of the prefixes pico and giga? Pico is 10 to the minus 12, giga is 10 to the 9, so you can see it's option C. You just have to know those. So we've got a diagram of a circuit. Okay, so all the resistors are identical and the meters are identical. A1 reads 2 amps and voltmeter V1 reads 2.5 volts. What are the readings on A2 and V2? Okay, so if we use V equals IR, we can calculate essentially what the resistance is for the top resistor, or in fact any of them, because we know the potential difference across the 2 in parallel must be the same, i.e. 2.5. We know the current through one of them, so we've now got what R is. We also know that the total resistance is going to be 1.5 R, because when you have 2 identical resistors in parallel, you end up with half the resistance, or R over 2, and you add that to the separate resistors, we get 1.5 R. So what we can do is we can calculate an expression for V2 in terms of the current and the total resistance, and we can see we end up with 6R. We know what R is, and we see V2 is 7.5, so we can see that it's going to be option C. Would be the reading on A2, because we're going to have, if we have a current of 2 going through A1, we know there's also a current of 2 going through the other parallel loop, giving us a total of 4. That's where the 4 comes from. Okay, so we've got a moving coil ammeter with its scale illustrated to measure the current. Full scale deflection is 10 amps. The meter has a systematic error as shown when the current is 0. So this is called what we call a zero error, which is a specific type of systematic error. Use this example to explain the meaning of systematic error. So it's an error which takes predictable values, which means we can then take the reading that we get and we can remove the predictable value and then get the accurate value. Just one thing I'll flag up, very commonly systematic errors, especially one like this, is the same value every time, but it doesn't have to be, it just has to be predictable. So if the meter has a reading of 6.5, what's the actual current? Well, when it's got a current of 0, it's on minus 0.5, that must mean it's actually reading 7 amps, because the reading is always 0.5 below what it should be. So a solar cell generates electrical power in constant bright sunlight. A circuit is required to measure PD and current delivered into a variable load resistor. So let's draw a diagram of that. So there's our variable load resistor, and here is our voltmeter to measure its potential difference. Fairly straightforward. Okay, so the solar cell is placed in constant bright sunlight. The graph shows the variation in potential difference with current. So describe how the potential difference varies as you draw more current. So the potential difference slowly decreases at a constant rate with respect to current. So we've got a straight line section where it's decreasing, and then it suddenly drops to 0 between sort of 50 and 55 milliamps. Suggests a reason for the variation. So our cell is only receiving fixed power because the sun is delivering a certain amount of energy every second to the solar panel. So if your current increases, potential difference must decrease, using this idea of P equals IV. And the other thing that we could use to explain this is the cell actually has internal resistance. So as your current increases, the terminal PD decreases as well. So that might help us understand what's going on too. So the maximum power from the cell is gained at point A. Calculate this power. So we're just going to use P equals IV, take some readings off the graph, but remember to convert from amps into milliamps into amps even. At points B and C, how do the values of the graph suggest the power delivered is lower than at A? Well, at B, we've got a much lower current for a very similar potential difference, so that's going to give us the lowest power. C, we've got exactly the opposite. We've got a much lower potential difference for a similar current, so again, that's going to give us much lower power using P equals IV. Okay, so looking at combining resistances, so we've got a diagram with a current of 7 milliamps flowing through, and we've got no internal resistance to worry about. What is the reading on the ammeter? So you can definitely solve this by thinking of this as a current divider. So 4 times as much current is going to go through the 1 amp as goes through the 4 ohm resistor, and twice as much current is going to go through the 1 as the 2 ohm. And you can fiddle around with ratios and get to an answer. But I'm going to show you a different way of doing it that kind of gets us to apply our rules. So the total resistance of this circuit we can calculate because they're in parallel with one another. So that's quite straightforward. And then we know the current going through the whole section, and we now know its total resistance, so we can actually figure out the potential difference across the resistors. And then once we've done that, we know the potential difference, we know the resistance, so we can figure out the current. And so if we go back to the way I was talking about to start with, this would mean 4 milliamps was going through the 1 ohm resistor and 2 milliamps is going through the 2 ohm resistor, giving us a total of 7 milliamps, so that works and that makes sense. 3 identical 8 ohm resistors are arranged in different networks. Which network has a total resistance of 12? Okay, so I'm going to use 2 rules to solve this. So series, you add the resistances together, and that's going to help us get rid of one of the answers here. And when you add parallel resistors, it always produces a total resistance less than either of the parallel resistors. So if we have a 1 ohm and a 2 ohm in parallel, the total resistance will be less than 1. It's got to be less than both of them, and that's going to be useful here. So we can eliminate A straight away. That's clearly got a resistance of 24 ohms. Circuit B we can get rid of because it must have a resistance less than 8 ohms. Likewise, D we can get rid of. It must have a resistance less than 8. It will be actually 8 over 3. So we're kind of left with it must be C. If we have 2 8s in parallel, that gives us a total resistance of 4. Add that to 8 and we can see we get 12, so that works. So the diagrams, we've got identical resistors. Which network has the lowest resistance? Hopefully it's fairly obvious it's not going to be A. Series circuits always have the highest resistance. B, that's got a total resistance of just 1 resistor by itself, because each of those parallel sections have R over 2 total resistance. Add them together, we just get R. So essentially that's just basically 1 resistor. C and D, we can see, are both going to be more than 1 resistor. C is going to be slightly, it's going to be 1/3 above 1 resistor. D is going to be like 2.5 resistors. So they're both clearly bigger than 1 resistor by itself. So B has got to be our answer. So the diagram shows 4 resistors connected in a square. An ohm meter measures the resistance between different points. Which point will the ohm meter reading be the smallest? So I'm going to use the fact that the resistance is always less than the smallest resistor in your parallel. So whichever connections we put it across, we want to choose the one with a pathway with the lowest resistance. So I would put it between P and Q, because that gives us a total resistance that must be less than 2 ohms. If we pick any other way of connecting them, we're going to end up with a higher lower bound for it. And you can actually try this out and plug numbers in to test it out if you want to, but we're going to end up with Q when you plug the numbers in. All the resistors in the circuit X, Y, and Z are identical, which list shows the circuits in order of increasing resistance. So looking at them, X has got them all in parallel, so that's clearly going to be the lowest resistance. So we're starting with X, so it's got to be A or B. And then if we look at it, Z must be less than 1 resistor by itself, because that's one of the parallel options, whereas Y must be bigger than 1 of the resistors, because we've got sort of like a half plus 1. So it's going to go X, Z, Y. So a long piece of wire has a resistance of 2 ohms and it's cut into 40 equal lengths, and these are connected in parallel. What is the resistance? So first of all, let's get the resistance of just 1 resistor. So we've chopped up into 40 equal lengths. That gives us a resistance of 1. And then if we put them in parallel, we essentially are going to divide that by 40, and we get the resistance option A once we round it to 2 significant figures. Conducting putty is a soft material which can be easily made into different shapes, and it conducts electricity, hence the name conducting putty. So we've got 50 grams of conducting putty between two metal plates, and this arrangement has a resistance of 8 ohms. The plates are squeezed together, so the distance between them is halved. What is the resistance now? So the key thing to realise here is it's not just the length that changes, it's also the cross-sectional area. And if we keep the same volume of putty, if we halve the length, we must double the cross-sectional area to keep volume the same. So we've got double the area and half the length, so we're going to quarter the resistance, so we're going to end up with 2 ohms. A wire has length L, diameter D, and resistivity ρ, and resistance R. Which wire of the same material has resistance 4R? So remember, we can increase the resistance by either increasing the length or decreasing the area or decreasing the diameter. So if we look through our options here, if we keep length the same, that's not going to increase the area. But if we halve the diameter, that's going to quarter the area, which is going to multiply the resistance by 4. So we can see with the first option, that one is correct. All of these others are going to produce different ones. B would multiply it by 16. C is going to, I don't know, it doesn't matter really. We've got our option anyway. So a composite wire is made of connection in series 4 uniform bars made of the same material but having different diameters. So the resistance of the wire is measured between X and other points on the wire, and then it's plotted as a graph. Which graph best represents the relationship? So I'm going to sort of break it into 4 sections. So if we increase the length while staying on X, we're going to get a straight line graph, but the resistance is going to be increasing. So we can already eliminate C and D because they show resistance is constant as we increase the length, and that's just not true. And then once we cross over onto the smaller section, each unit length is going to have a bigger resistance because it's got a smaller diameter. So I'd expect to get an increase in gradient as we change to the thinner one, hence why I'm going to pick option A, and it's because we've made it narrower. A copper wire of length 3 meters has resistivity of this value and resistance 15.9. What is the diameter? So this is the equation we want, and in place of area I'm going to put pi d squared over 4. And then we rearrange to make D the subject, plug the numbers in, and we get our answer, which is option D. So it's just some rearranging here. 4 lamps have filaments made of the same material. The lamps are connected in parallel across a battery. Which filament lamp transfers the most energy into heat and light per second? So we're essentially going to need to use P equals I squared R. So essentially, we're going to want the one that has the biggest current, essentially. So the first thing I'm looking at here is options A and options D are clearly the same. So since we can't give 2 answers to the question, it can't be either of those, because those 2 factors of 2 would cancel each other out. B would give you twice the resistance but half the current, so that will give you lower power. Option C gives you half the resistance but double the current, so it's clearly going to be option C. The following measurements of a uniform metal wire are taken so resistivity can be calculated. Okay, so we've got some values with their uncertainties, and the equation we're going to use is the one we've been using so far. State which measurement has the greatest effect on the uncertainty in the calculated value of ρ. So since it says state, this question is clearly not expecting us to do any calculations. So the answer it's looking for is diameter, and the reason being is because diameter gets squared, so you have to double its percentage uncertainty. I found that quite annoying because I decided I would check the calculations anyway, and we can actually see the correct answer from the values is actually R, but we wouldn't know that without doing the calculations. So the answer it's looking for is on the left, but this question is annoying because the numbers actually contradict that. So we're looking at a demister in a car, and we've got a conducting material fused onto the glass surface, and you can actually see this if you look at especially they're usually on the back windows, they're not usually on the front. So we've got 10 conducting tracks, and we're trying to decide whether we want them in series or parallel. So we want to draw a series. It's going to look like this. We're going to connect them end to end, and then all the way back round. And then parallel, much easier. We're just going to connect all the ends together to the terminals of the battery, a little bit like this. Okay, so to demist effectively, each track needs a power of 24 watts, and we've got a battery at 12 volts DC. Okay, so if they're in series, they're going to share the potential difference between them. There are 10 of them, so we're going to get 1.2 volts each, whereas in parallel, they're each going to get 12 volts. But that being said, in parallel, they're going to divide the current between them. So we've got 24 watts split between 12, gives us 2 amps each, whereas in series, what we're going to get is each one is getting 24 watts. We've got a potential difference of 1.2, so it gives us a current of 20. So we're essentially using P equals IV to calculate these values. And then using V equals IR, we can then get the resistances using PD and current there. So we use P equals IV and V equals IR for the last 2 rows, and then just use our Kirchhoff's second law for this first row. So material from which the tracks are made has this resistivity, and this time we're modelling them as a rectangular cross-sectional area, so we're not going to have any pi's or d-squareds in here. So we've got length and thickness, and we want to know what their width is. So resistance is calculated in this way, and instead of area, I'm going to put width times thickness. So we want the width, so let's make that the subject, plug the numbers in, and we get the width of 2 millimeters once we round appropriately. Would you choose a series or parallel connected tracks? I choose parallel, and I think there are 2 reasons. One, if one of your wires breaks, that doesn't destroy your whole heater, so you don't end up with a completely fogged up screen. That's fairly useful. And the other thing is that in parallel, each wire can have a larger resistance. We saw it was 6 as opposed to 0.06 or something like that. And larger resistance means it can be thinner, because remember, the thinner we make our wire, the higher resistance is, and that's going to mean you can see more out of your window. Calculate the resistance of copper wire, length 500 meters. We've got a diameter this time, so very similar to what we did before, just using the resistivity equation and putting pi d squared over 4 in place of A. And that gives us our value of resistance. So the diagram showed us a small heater, and it's 12 volts, 20 watts, calculate its resistance. So we've been given potential difference and power. We want resistance, so we'll just rearrange this equation, gives us the resistance of the heater at this particular power potential difference rating. Okay, so the heater is connected to a 12 watt supply with no internal resistance, like this. So we can see we've got a total of 500 meters of connecting wire, so we can use our previous calculation here. Calculate the power the heater supplies in this arrangement. So I'm going to work out the current and then work from there. So we know the potential difference that's supplied. We know the total resistance because we've calculated the 2 separately, and we can see that we end up with this current, and then using P equals I squared R, that gives us the heater power 2.5 watts. Okay. So the same connecting wire is then used to a different heater with a power supply of 100 volts, and it's again no internal resistance. So we've got 100 volts, 20 watts. Explain why less power is wasted in the connecting cables compared to the previous one, and we are expected to do a calculation here. So using P equals IV, we can work out what the current is. If we know V is 100, P is 20, that gives us the current. But previously our current was 0.6, so we've divided the current by 3. So then P equals I squared R, we've still got the same connecting wires, so their resistance is the same. So long as their temperature remains about the same, the power dissipated will be about 1/9, because current was divided by 3, so current squared is divided by 9, so we got a much lower value. So flow occurs in many different areas of physics. For example, flow of electrons is an electric current, heat flow takes place with a temperature gradient, and water or gas flowing along a pipes, that's caused by a pressure gradient. The dimensions of a material through which the flow occurs, together with the properties of the material and the cause of the flow, determine the amount of flow that takes place. Explain why one pipe is necessary for a supply of gas, but two are needed for electricity. Well, this is due to a conservation law. So in a circuit, we know charge must be conserved. So if a charge goes into a house, a charge must come out of the house, which is why we need two wires. Whereas with something like gas, gas is consumed because let's say we're doing cooking, we're combusting it or burning it and turning it into water and CO2. That escapes into the atmosphere, so we don't need a way back for it to flow. We can just have it flowing straight out into the atmosphere. So the rate of flow of heat energy through the wall of a room is given by this equation here. So we can see it can be increased by temperature difference, it can be increased by having a bigger area, and it can be decreased by making the wall thicker. All of those things kind of make sense. And then we've got some sort of constant there. So deduce the SI unit of K. So what I'm going to do is rearrange the equation to make K the subject, and then substitute in the units of what we've got, cancel out some meters, and we end up with the unit of K. Okay, so the temperature inside the room is 22 degrees Celsius, outside temperature is 8 degrees Celsius, the value of K in SI units is 0.35, calculate the rate if we have the thickness and the area. So basically it's just asking us to plug numbers into the equation, gives us a value of 590 watts to 2SF. So write an equation analogous to that in B for the rate of flow of charge. So our equations should be in terms of potential difference, resistivity of the material, and then the length and cross-sectional area. So I'm imagining this that K, the constant, is going to be analogous to conductivity. That's kind of our constant involved with the flow of current. We've got delta T is going to be analogous to potential difference, and then D is going to be analogous to like the length of the conductor. So then we get this expression here, but it asked us to have it in terms of resistivity, so we can put that 1 over resistivity in place of conductivity to give us the expression we're looking for. Comparing the equations in C and B, state which thermal property corresponds to V. Well, I already said it, it's temperature difference. And state which thermal property corresponds to resistivity. It's clearly 1 over K. And then finishing off, the rate of flow of gas through a pipe may be measured in centimeters cubed per second. Suggest an equation for the rate of flow of gas, again identifying any symbols. So flow is caused by a pressure difference this time. We're going to have a constant of some kind, so I think we're still going to be impacted by the area and by the length of the pipe, so this is what I reckon the equation would end up looking like. So then we've got a flow rate of 160 with diameter 15. Calculate the flow rate if the diameter is 22. So essentially the diameter 2 we can express as 22 over 15 times D1. So then the area we can express as 1.46 squared times A1. And then once we've got that, we can multiply that by 160, gives us the flow rate of 340, finishing off this video.